So as we talked about on large industrial consumers like manufacturing plants often operate at a power factor of less than 1 due to the presence of numerous inductive loads like electric motors. To avoid being fined by their distribution utility, a technique known as power factor correction can be employed to raise their operating power factor to an acceptable level. So let's say that we have an industrial consumer and their load prior to power factor correction, the complex power absorbed by their load prior to power factor correction looks something like this, okay? So since it's going to be mainly inductive loads that we're going to see, I would expect that I would get a positive phase angle. And so I'm going to say that S old, which is the complex power before power factor correction, is going to look something like this. Its projection onto the real axis will then be P old, because that's the real part of it. And its projection onto the imaginary axis will be Q old. And the angle formed will be theta old, like so. All right. So if I want to increase the power factor, what do I want to do to that angle? Do I want to make it larger or smaller? Smaller, okay? So I can make that angle smaller by injecting some reactive power into the system, okay? So let's say that I include a capacitor that adds this much reactive power. So I'm going to call this guy Q cap. If I add these vectors tip to tail, my resultant is this guy right here. So let's call him S nu with an angle of theta nu. Okay. That is all that power factor correction is. You have a load that is consuming too much reactive power. So you hook a capacitor up to supply some reactive power, and your overall power factor decreases. Or excuse me, your overall power factor increases because that angle decreases, right? So our load in this case is still absorbing the exact same amount of average power, but only the imaginary part has changed. Okay, that's very, very important, because if the real part of the load changes, we have a very significant problem because it's not going to behave in the same way. All right. So this is how power factor correction works. Now we need to figure out what size of capacitor that we need to put in to figure out how this thing, how to reach a specific level. Okay. So we could say that S old is equal to P old plus JQ old. S nu is equal to P old plus JQ nu, and therefore the complex power supplied by the capacitor is just S nu minus S old, which will be exactly J Q nu, sorry, minus Q old. So this tells us the amount of reactive power that the capacitor needs to supply. Now we need to figure out how to relate that to our value C that the capacitor will have. Well, we developed alternative relationships for the complex power absorbed by capacitors, inductors, resistors, and all that kind of stuff at the end of class on Monday. So as a very, very brief recap, the complex power absorbed by a capacitor was found to be negative J omega C multiplied by the effective voltage drop over the capacitor squared. So we can literally put these guys together and we have the means to tell us what capacitance value we're looking for. So from that, we can say that C is equal to negative Q new minus Q old divided by omega VRMS squared, which is the exact same thing as P old times the tangent of theta old minus the tangent of theta new divided by omega VRMS squared. So this result right here directly tells us how to size a capacitor. If we know either the reactive power that the capacitor needs to supply, or literally just the power factor angles that we started with and the one that we're aiming for. Okay. So, as an example here, let's say that we have the following system. We have an industrial voltage of 400 angle 0 degrees volts RMS operating at a linear frequency of 50 hertz, and it is powering an industrial load like a motor. Our motor draws 1 kilowatt of power at a power factor of 0.80 lagging. And we want to know the size of C that is necessary to improve PF from 0.82 0.8 lagging. That is very important. To 0.975. Let me save this and restart because my computer is being dumb. All right, so I'm going to have this set up in such a way that we can literally see the equation we're supposed to use and try to figure out what bits of information we have and what bits of information we need to find. So, which pieces of information do we have? Anybody? Pardon? Yeah. Okay, so P old. The suggestion is that we have P old. I disagree, or excuse me, I agree. What is it? 1 kilowatt. All right. Absolutely correct. What else do we have? Okay, so we have the frequency. So omega is just going to be 2 pi times 50 hertz, or 100 pi radians per second. All right, what else do we have? VRMS. What is it, Ian? All right. So what are the two things we don't have? Yeah, theta old and theta new. So theta old is just going to be the inverse cosine of the old power factor, right? Because the power factor is defined to be the cosine of the power factor angle. So if we have the power factor and we want the angle, we just do the arc cosine. Anything wild or crazy about that? I certainly hope not. So what is the inverse cosine of 0.8? Should be something like 36.87 degrees, if my memory serves me correctly. Yeah. Theta nu is just going to be the inverse cosine of the new power factor. So the inverse cosine of 0.975. So that will be 12.836 degrees. So this isn't addressed in this particular problem, but what if I wanted to determine the capacitor that would take me to 0.975 leading? No. So we are going to wind up overshooting it, which means we're going to wind up needing a larger capacitive value. But where that's going to come into play, so right now, because I have two lagging power factors, both of my angles are lagging. If I had a leading power factor, that angle associated with the leading power factor would have to be negative, because negative power factor angles always give us a leading power factor. Okay, so if we were specified with 0.975 leading, we put a negative sign here, which translates to a negative sign there. That is literally the only difference whatsoever. Whenever we have a negative power factor angle, we have a leading power factor. Whenever we have a positive power factor angle, we have a lagging power factor. Always, always, always. So if we need it in the opposite direction, anytime we are trying to hit a leading power factor, we are forcing that power factor angle to assume a negative value. And we accomplish that by overshooting, which is what Ian mentioned. So we literally have all of the information required to plug into our equation. So we would find that C is equal to 10.387 microfarads. That's all power factor correction is. Put a capacitor in parallel with your load to make it absorb less reactive power. So let's do the lab. Unless if people got questions, I'd be happy to answer it, but we're an hour into class already. Okay, anytime we have a lagging power factor, our power factor angle will be positive. Anytime we have a leading power factor, our power factor angle will be negative. Lagging power factor is positive angle, leading power factor is negative angle. Stephanie. Pardon? Putting all of these values into that equation. Kyle, you got a question? Okay. Anybody else have any questions or anything? All right, so we have a lab to do today, and then on both Friday and next Monday, we will have review sessions where I will spend roughly 4 hours answering any questions that you may have about any circuit analysis topics that you may feel uncomfortable with, because our final exam is cumulative. Now, Dr. Swanbaum and I conversed before class, and he officially asked if we could have an equation sheet, which means we will have an equation sheet. I'm going to do my best to get that equation sheet out to all of you guys so that you can see it and all that kind of stuff as soon as possible. I am leaving it up to Dr. Kronk to make, because he's already made one before. So hopefully we can just take that and I'll make a few edits because I think there was a couple of mistakes on there or something last time, and I'll put it up. So the equation sheet that you will be using for this exam will be provided to you by like with the exam or whatever. So you do not get to write your own equation sheet and bring that to the test. It will be provided to you. At a minimum, it will include all of these power factor, like the complex power relationships and all that kind of good stuff, because I hit you guys with like 47 equations in 2 days. I absolutely understand that that's a lot. So there's definitely going to be those on there. Like I said, I'm going to try to get it, at least a draft of it or whatever, to you as soon as possible so that you can look over it. I may decide to include more information, in which case you will be pleasantly surprised when you see your exam, but it definitely will not contain less information than what I present to you. Okay? Elijah. Compared to the exams that you have had in this class, I would say that it should fall somewhere in between the difficulty of exam 1 and exam 2. Okay. I never try to make an exam intentionally difficult, although you guys, I'm sure, wildly disagree with that statement. But truthfully, I try to make all of my exams and stuff like that as straightforward as possible while testing your ability to do what I want you to do in this class. Whether or not you find that difficult, I believe directly correlates to how much attention you've paid in my class. But again, I'm a jerk with a PhD, and so all of this stuff is easy to me because I've got 15 more years of practice than you do, okay? I 100% believe that all of you are capable of doing well on any and every test that I give, or I wouldn't give them. But, you know, stuff happens. Like, people make careless mistakes, and unfortunately, the format that we use with multiple choice exams does not have a lot of tolerance for careless mistakes and things like that. So I've tried to warn you in advance of the kind of tricks and stuff like that that I like to pull, such as if I ask you to calculate power, you need to know the difference between absorbed and supplied to know whether or not it should have a positive sign or a negative sign. I have told you directly that I will ask you for you know, the reactive power or something like that on the exam, and I will give you the exact same numerical answer 3 times, once with units of watts, once with units of volt amperes reactive, and once with units of volt amperes, and I am expecting you to know what the difference between those units are, things like that. I don't think any of those types of questions are overtly difficult. If you were paying attention, I feel like it should be trivial, and if you weren't, then you'll be punished. I don't know how else to put it. So that is the level of difficulty I strive for. if you were paying attention and practicing by doing your homework and working on the in-class assignments and all that kind of good stuff, I truly feel that my test should be rather trivial for you. But I understand completely that I have a lot more practice than you all do. And you guys, I don't want to say have more going on than I do, but definitely more going on that would prevent you from learning circuits to the degree to which I understand it at this present time. So anywho, lab stuff. Go do the work.
How's the conference?